This is May 2009, A22 Physics 5, question 3A. Now 3A, part 1 and part 2 are not on anymore, and so you don't have to do those about specific charge. And we're just going to leave those. Part B, you can do the next bit, however. The specific charge of an electron may be measured by passing a fine beam of electrons through an electric and a magnetic field which are at right angles to each other and the path of electrons, and this is called crossed fields. Figure 3.1 indicates a fine beam of electrons travelling perpendicularly outwards from the plane of the paper between two metal plates which create a uniform electric field. On figure 3.1, mark the polarity of these plates to create an electric field and mark clearly using an arrow head labelled E the corresponding direction of the electric field. Mark clearly with another arrowhead the direction of the corresponding magnetic field B, which would be needed to produce null deflection of the electron beam. Now it doesn't tell you what direction that the electrons are moving in, so all you need to do is mark one negative and one positive. In fact, I'm going to put plus here and minus here. And I'm going to draw an arrow in, and that's the direction of the electric field, so it should be a nice straight line across there. And that's the electric field. So then you have to work out, right, if you have a beam of electrons and they're coming out of the page, then they're going to experience a force towards the positive particle this way, the positive plate this way, of course. But something must be stopping them. They must be experiencing a force the opposite direction, which leaves them in the centre of the two plates. And so you have to use, so when you have to determine the direction of the magnetic field, the electrons are coming out of the page towards us. Now, if you use your left-hand rule there, that means that your current is actually moving into the page like that. You know that the electrons will be attracted over towards this plate, so therefore they must be experiencing a force to the left. So I have to turn my hand round to get my force finger, which is my thumb. So my beam of electrons, the direction of the current is into the page, and the force is in this direction here, and therefore that leaves my other finger, which represents the direction of the field, upwards. And so I'm going to draw an arrow on here like that, and those are the crossed fields there, and that's the B direction. Now you could do this the other way round. If you'd mark that negative and that positive, that would mean that your electric field is going in the opposite direction, and your B field will actually work out that it's actually going down the way. The next question says, a beam of electrons is replaced by an identical beam of positrons. State and explain whether this beam will still experience null deflection for the E and B fields you have indicated. So the answer is yes, it is still a null field. And that's because the positrons will move left. In my diagram, they'll move left towards the negative plate. Sorry, they'll move actually right. Move right towards the positive plate, the negative plate, even. And then the B field will move them down the way. We'll move them left. So the B field will move the positrons left, and therefore there will still be a null field happening there. Last part of the question. A fine beam of electrons moves through a region where an electric field and magnetic field act perpendicularly to each other. The electrons in the beam are not deflected when passing through this region. The magnetic field has a flux density of 1.5 by 10 to the minus 3 teslas. The electric field strength is 1.78 by 10 to the 4. Calculate the velocity of the electrons in the beam. So F is equal to EQ, or E is F over Q, and that's the electric field, the force due to the electric field, and that's equal to the force due to the magnetic field, which is BQV. The Q's cancel each other out, and therefore when we're looking for velocity, velocity is going to be equal to E divided by B. And E is 1.78 by 10 to the 4, and B is 1.5 by 10 to the minus 3. And that gives you an answer of 1.19 by 10 to the 7. So it's 1.19 by 10 to the 7 meters seconds to the minus 1.